Hello, wonderful people. Here we are in chapter 33, Electric Fields and Potential. Up there. Um, I'm going to do something a little different in this chapter. I'm going to race through the beginning here. So we're not going to do section 1, 2, 3, 4 over the next 1, 2, 3, 4 days. I'm going to do sections 1, 2, 3, 4, and half of 5 in this video. Correspondingly, the day's assignment will still only have 2, 3, 4, maybe 5 homework questions. And then because I want to get us right into voltage. For those of you who have heard of the word volts, that's an electrical term. And once you start talking about those kinds of electrical terms, volts, amps, resistance, then you're into the part where you can talk about electricity like technicians do, like the guy who fixes your electronics on your car, or the person who fixes something that's wrong with your electrical wiring in your home. That's the language of everyday ordinary electricians. And that's the language that I really want you to learn and be familiar with, so that when you have electrical issues in the rest of your life, you are able to talk about them and figure them out. And I'm not saying you're going to fix it yourself. I just want you to be able to understand what's going on so that you can make intelligent decisions, because they will try to charge you too much if they can. And knowing what you're talking about is how you fight back against that. So that's what I'm after. So let's see if we can get through this first half of this chapter 33 in one fell swoop. I promise I'll be gentle. Okay. What is it like to feel a gravity field? If you throw a ball upward, it follows a curved path due to the interaction between the gravity of the ball and the Earth. The two objects, the ball and the Earth, are far apart, so this is action at a distance. The concept of a force field explains how Earth can exert a force on things without touching them. The ball is in contact with the gravity field all the time. This is, of course, everyday life. We're used to walking around the surface of the Earth and being held down by the gravity field. What is it like to feel an electric field? You can sense the force field that surrounds a charged Van de Graaff generator. And oh my gosh, I wish you could be in the classroom, because that is a fun little display. To charge up the generator, which looks like a big metal ball there in the picture. And if you're standing just a foot away from it, you can feel the charge in the air. Your hair stands up and you feel the charge. An electric field is a force field that surrounds an electric charge, or a group of charges, not just one little positive charge, but, coulombs of charge. A gravitational force holds a satellite in orbit around a planet, and an electrical force holds an electron in orbit around a proton. The force that one electric charge exerts on another is the interaction between one charge and the electric field of the other. So that's just explaining what the electric field is. Just like a gravity field, an electric field is what causes the negative electron and the positive proton to have a force on each other. So we need to figure which way is up as far as electrons and protons go. With gravity, it's easy. Down is the way that something falls when you let it go. But because there's positive and negative charges, we just need to pick a direction and stick with it so that we're all talking about the same thing. So this is the way we set it up. The direction of an electric field at any point, by convention, what we all decide, is the direction of the electrical force on a small positive test charge. So, if the charge that sets up the field is positive, then the field points away from the charge. If the charge that sets up the field is negative, the field points towards that charge. and we definitely need examples for this. So here is my positive charge, my small positive test charge placed here. Bang. Now over here, I have object B that has a whole bunch of negative charge. So what's this positive charge going to do? It's going to fall inward towards the negative charge. So that's why these field lines that I'm drawing for this negative charge point inward. And now for a positive charge on object A, there's my small positive test charge placed here. Now what's going to happen to this positive charge? Well, this positive charge is going to push this away. So that's going to move outward, away from object A. So that's why the field lines point outward on a positive. Now, could I have gone inward on a positive and outward on a negative? Yeah, we could do that. But this is the way we chose it. So once we chose it, we're sticking with that all the way for the last 200 years. Finally, if I have object A and B, the positive and the negative, next to each other, you can see the positive, the electric field lines coming out of the positive and then going into the negative. And that's the way it works in real life. The positives are attracted. And if there's nothing to stop these, they're going to pull on each other until they meet in the middle. Yeah, so these are the electric field lines. That's the title of this part of the lesson. And this is how we draw them. So, then we've got a charged plate. So the plate, the positive side goes out of the positive and then into the negative. That's the direction of the electric field. So if I drop a small positive test charge in the middle of this field here, it's going to move to the right. It's going to follow the field line. Okay, and now some real world examples. Let me just read this. You can demonstrate electric field patterns by suspending fine thread in an oil bath with charged conductors. The photo shows patterns for equal and opposite charge. So this is, I don't know if this is the positive or negative, but that's the opposite. And you can see the field lines in the picture. So if you put a small positive test charge right here, and let's say that the negative is on the right, you can see how it's, disappeared on me. How a positive charge is going to move along this field line and follow it in until it, bang, hits the hits the negative conductor, because positive would go towards negative. So this is exactly what it looks like in space. Those threads are showing the field lines. Pretty cool. There is when the two charges are the same. So they're being repulsed. So this line goes up and off to infinity because this is a positive charge and that's a positive charge. And if you let it go, if there was nothing holding those in place, they would push away from each other. And please note, if you had a positive test charge right there, smack dab in the middle between the two, at exactly the right point, it would stay still. Now, if you just nudged it the tiniest bit, it will move away from there. So, it's like balancing a ball on the top of a knife. It's hard to balance, but it is theoretically possible. But don't try it in the real world. Okay, and then finally we have another picture, charged plates that are opposite charges. So it's going from one side to the other, and you can see how they start to bend out when the plates run out. And then this one is a circular conductor and a plate that are opposite charges. So here the lines are straight, right there, right in the middle it's straight, but everywhere else it starts to bend a little bit. And even these lines back here will come out and around and all the way around. Pretty cool, huh? Bits of thread, said that. So here's something interesting. This is a lightning bolt generator. And this is somewhere in Detroit where they test cars to see what happens when they're hit by lightning bolts. This is lightning coming off that generator and it hits the car, and you don't see where it goes to ground, but in the back of the car It goes from the metal shell of the car, and then it comes out of the car and down to the ground. Why? Because it doesn't go through the tires. The tires are rubber, and rubber is a very good insulator. So let me read this text. When a car is struck by lightning, the occupant inside the car is completely safe. The electrons that shower down upon the car are repelled, mutually repelled. So they spread out over the metal surface of the whole car. And then eventually it gets to the bottom and discharges when an additional spark, a second spark, jumps to the ground. So we've got the spark from here to the car, and then in the back it's going from the metal car to the ground. The electric fields inside the car practically cancel to zero. So if you're in a car that gets hit by lightning, you're never going to be hurt. That is completely true. So that means you can shield against electricity. But you can't shield against gravity because gravity only attracts. Shielding only works when there's a positive and a negative. And it's pretty easy. Shielding electric fields is quite simple. Step one, surround yourself, or whatever you want to be shielded, with a conducting surface. So you can wrap yourself in aluminum foil. And then put that surface, the metal foil, in an electric field of whatever field strength, 10 volts, 100 volts, whatever. The free charges in the surface will arrange themselves so that the field inside the conductor is zero. I'm not asking you to be able to explain that. All I'm saying is that if this surface is a conductor, then inside there is no electric field. You can see the electric field lines out here. There's lines everywhere coming off this conductor and off this conductor. But inside the conductor, there is no electric field. Okay, so to summarize, this is the showing you the electric field all around that circle and all around this plate. Even these lines down here, lines down here are going out and around to this conductor. But inside of the conductor, you don't see any lines. They're all just little dots. The threads aren't all lined up like left to right or up and down, because inside any conductor, the field strength is zero. We'll talk more about that next week, but that's good to know for right here, right now. But this also means that so here's a conductor and a wire, and this wire is going into this electronic component. And there's all kinds of data that's going through this wire. So if you want to protect this wire so it doesn't get any kind of interruptions, if there's a lightning strike or nearby, or if you put this next to some other wire that has a lot of current, to shield this conductor, then you have the plastic that protects this wire. But then you just put a metal foil around it. And this metal foil, the metal cover, shields the cable. So this metal foil shields the copper conductor from any kind of outside electrical fields. And the same thing with this component, whatever this is. The cover up here has metal foil on the inside of it, so it protects this circuit board and all the components the same way. So you can have electric shielding to stop electric fields from getting into things. Okay, I think I can stop it there at 33.3, and we'll pick up with 33.4 tomorrow.